Okay, if you take a pail of water and you spin it around in a circle over your head, it's possible to spin it fast enough so that the water doesn't come out and fall all over you. The question here is, so how fast do you have to spin it given a certain radius? So they tell us here to start with a free body diagram. All right, so let's take a free body diagram of the water at its highest point. We'll actually take a free body diagram of the whole pail. We'll free body diagram the water. I'll just show the pail. So free body diagram of the water at the top. So here's the pail, right? And inside it we have the water. Okay? And this is what I want to free body diagram, and this is really what I'm interested in. I don't care so much about the pail. I'm interested in the water not coming down on me because I have my handle on the pail, right? So we should identify what sort of forces act on it, and what kind of result of these forces, accelerations, etc. I'm going to choose. I have here some of the things I know, like a centripetal acceleration is going to have to be down like this. I have a weight down like this, so maybe I'll have my coordinate system with a positive downwards, and then to the right is pretty arbitrary here, but I'll take a positive y to be downwards. Other forces I have acting on it, there's a normal force, right? There's a normal force between the bucket and the water, right? I mean, there's a contact there, so there must be this push or pull. And I'm free body diagramming the water, and so I want to draw the forces act on it. What is the normal force exerted by the bucket on the water? Well, the bucket is over here on the outside, and the water is on the inside, right? So I have the normal force exerted by the bucket on the water is pushing down like this, right? That would be our normal force. Okay? So we have, these are the forces which act on the water. I take that bucket away, and here we have just the free body diagram of the water at the top. Okay, so I know that it's in a vertical circle, so when I sum the forces in the y direction, I get mass times acceleration in the y direction, which is my mass times centripetal acceleration, which is positive because I call positive downwards, right? All of these are actually positive: the normal force, the weight, and the centripetal acceleration. So we have the sum of the forces are normal force plus the weight equals the mass times the centripetal acceleration, right? So we can say here that the normal force is the mass times the centripetal acceleration minus the weight, right? Just some algebra there. And now when you think about just the physics here a little bit, if I want this water to stay in the bucket, what does that mean about the normal force? The normal force can't possibly pull. The bucket can't pull the water upwards, not the way it is here, right? Not with this bucket being upside down like that. I mean, if it was at the bottom, sure, it can pull it upwards, but not like this. The bucket can only push on the water here, right? So the normal force can only push. And I would never want the situation where I would need the normal force to pull, because it can't do it, right? So my normal force always, it needs to be greater than or equal to 0, right? There needs to always be a normal force. If I don't have a normal force, I don't have contact, right? And then I have water falling out. That's basically the way it goes. So the normal force has to be greater than or equal to 0. But the normal force is this, right? So that means that the mass times centripetal acceleration minus the weight must also be greater than or equal to 0, right? I mean, because this is the normal force, yes? Okay, so, I have a mass in both of these. I can kind of factor that out. So I have mass times centripetal acceleration minus gravity must be greater than or equal to 0. Now my mass is always greater than or equal to 0, right? If I'm talking about negative mass, I have a completely different, problem here, right? So massless water is very dangerous. So the mass, I can divide both sides by m, and it's going to go away, right? So I must have here the centripetal acceleration minus gravity is greater than or equal to 0. Or, pulling this g back over, the centripetal acceleration is greater than or equal to gravity. This is what it comes down to. And when you think about it, it's sort of intuitive, actually. For something to stay in a vertical circle, right? So for this water to stay in the bucket in the vertical circle, the centripetal acceleration which is required for that circle, that's what centripetal acceleration is. The acceleration required for the circle has to be greater than that which gravity provides, right? I need to make it need more than what is given. That way there's still a normal force. If I have gravity greater than, or just greater than the needed centripetal acceleration, that means that I need a certain amount of centripetal acceleration here to stay in the path, but gravity pulls it down a lot more than I need, and the water comes out of the bucket, right? So this is how that speed comes in. I need to make sure what the acceleration I need is greater than what's provided. If I go on the moon, where gravity is like 1/5 of what it is on Earth, I can go much more slowly, which would be very exciting, right? Okay, so, if just looking at the speed here, we have the centripetal acceleration must be greater than or equal to gravity. This means that we have v squared over r is greater than or equal to g. Or I can say that v must be greater than or equal to the square root of rg, right? Doing a couple steps there. Okay, so it comes down to be pretty simple. It's just got to be going more than or equal to the square root of the radius times g, the acceleration due to gravity. And so we actually see here, for our problem, and I haven't really even done specifically our problem, just kind of came up with a general equation for this, and this is helpful for you to go through this derivation on your own. We had a radius of 0.6 meters. So, we can say here that our speed must be greater than or equal to 0.6 times 9.8, right? So then we would have our speed must be greater than or equal to 2.42 meters per second. And so, the minimum speed would be, just equal to 2.42 meters per second, right? So minimum speed is that. And like I said, if we're on the moon, I think this becomes like 1.6, right? So probably becomes about like half as much. You can plug it in there. It's probably right around 1.1, 1.2 meters per second. So kind of nice. You can use this later on. We'll actually take a look at, like, if you had a roller coaster and you're not strapped into the roller coaster, how fast you need to be going, and the upside down of the loop in the roller coaster. It's exactly the same way that you can do it. And later on, we'll say how fast you need to be going into the loop in order to have that speed at the top when we start talking about energy in the next chapter.